water. We sometimes take water for granted. I think we've been more aware of the value of water since we've been in a severe drought. But the chemical nature of water is also important and remarkable. Water has a low molar mass, 18.02 grams per mole. A lot of those other substances that we were comparing boiling points of were 30, which is larger than water. So water's a small molecule, but it's a liquid at room temperature instead of a gas. If we look at a graph where we're comparing hydrogen compounds with elements in different periods. So oxygen is in period 2 of group 6A. And sulfur is in period 3 of group 6A. Selenium is in group 4, tellurium is in group 5. For these three, they're compounds with hydrogen, we see a trend in the boiling points. We see that as the molecule gets larger because the central atom is larger, the boiling point goes up. And that's what the trend in dispersion forces tells us, that a larger molecule is going to be more easily polarized, and so the dispersion forces will be stronger. Stronger forces, higher boiling point. From this trend, though, what would we predict for water? We would predict that water would be down here somewhere, minus 100. What would life be like if water boiled at minus 100 degrees? Would we be alive? No, your body contains a lot of water. And it's not at minus 100 degrees. It's at 37 degrees Celsius. The reason that water has such a high boiling point is because of the hydrogen bonding. We've got a small molecule, we've got the oxygen-hydrogen bond, and so the hydrogen bonds in water are very, very strong. Water is a polar molecule. That allows it to dissolve a lot of other polar substances and a lot of ionic compounds. Water is sometimes called the universal solvent because it dissolves so many things. Most of the liquids that we are familiar with are actually solutions where water is involved. So I've got raspberry lemonade here, right? That's a liquid, right? But the liquid in it is water. We actually encounter very few substances on a daily basis that are liquids that don't involve water. Water in your body is the solvent for many chemical reactions. Your blood has a lot of water in it. I think we all recognize that without water, there can be no life. Apparently, there's been some recent evidence of water on Mars, which gets people very excited that maybe they're going to find evidence of life on Mars. I prefer to look at things on this planet, but that would be cool. The way that water freezes is unusual. Most solids are more dense than their liquids, but for water, it's the opposite. Ice is less dense than water. That makes ice float. That's pretty important. I mean, icebergs float, ice cubes float, that's nice and everything. But what's really important is that when water freezes on the surface of a lake, it doesn't sink to the bottom. If it did, the lake would freeze solid, and all the life, the fish, the turtles, everything in there would die if the lake froze solid. Instead, the water that freezes on the surface where it's colder floats, stays on top of the water, and actually insulates it from the cold atmosphere and keeps the lake from freezing solid. Growing up in Minnesota, where fishing is a major industry and tourism involving water sports, Minnesota would be done for if water didn't float. So if water as ice is less dense than liquid water, its mass doesn't change, so its volume must change. When water freezes, it expands, its volume increases. And this has a lot of impact on things. For one thing, have you ever stuck a water bottle in the freezer? Like, oh, I'm going to be good tomorrow. I'm going to have my water bottle, and this can be cold all day long because I'm going to freeze it. What often happens? It cracks. It breaks. Because as the water in the water bottle freezes, it expands, and freezing ice is actually very powerful. It expands, it can break metal pipes. It does a real number on the roads in Minnesota. Any little crack, water gets in there, freezes, expands, it just takes the roads apart like you wouldn't believe. So do not put full containers of liquid in the freezer. If you want to freeze something, you want to leave some space, and then the shape of the container can kind of be important too. This also has impact for living organisms. We're supposed to get a freeze tonight. And so a lot of the more sensitive plants are going to die. Why do they die? Have you ever seen hostas after a freeze? They look like wilted lettuce. They were fine yesterday, and now they just gave up in the frost. What happens? Well, the water in their cells expands and bursts the cell walls. Not a happy situation for the plants. This also explains why a lot of foods, like lettuce, don't freeze well, right? Or you can freeze them, but they don't taste the same afterwards. You let a frozen strawberry thaw out, and it doesn't have the same texture as it did before you froze it. Flash freezing can help because when they flash freeze fruits and vegetables, it freezes so fast that the water molecules don't have time to organize themselves in that open lattice pattern, and so that minimizes the cell breakage. Flash freezing involves suddenly freezing it very quickly. So just putting something in a deep freezer won't work. It has to happen really fast. That's how they make popsicles. They freeze them real fast. And that way the syrup doesn't separate.